So, welcome back. In the last video we have seen how to solve a Laplace equation in a annulus region. So, that we have seen the boundary problems inside a circle or exterior of the circle as a special cases of this annulus region. I also mentioned today we will have what we do is we will consider the sector part of the circle. So, that is the sector. So, in an annulus region we consider. So, in an annulus region we consider a sector. So, that means R is between R1 and R2 and theta is between some theta 1 and theta 2. So, this is the general domain. So, if we actually see that, so we will just look at the figure. So, if you see that this is the figure we see. So, theta 1 is theta 1 is this. So, 1 is the problem 1. So, 1 is the problem. So, this is the domain of the problem. So, inside, so whatever we have here. So, this is the part of the annulus region. So, if you consider this is your domain D. So, in this domain D, so you have a Laplace equation is satisfied. So, that means gradient square u equal to 0 and you see that at R equal to R1 and you have you can give the boundary data. So, you can think of a curved domain like this as a plate. So, and initially when it reaches a steady state. So, when the temperature reaches a steady state inside this domain. So, you can see that you want to see the temperature distribution and provided the boundary, at the boundary you have this temperature is maintained u at r theta, r1 theta is some f1 of theta. It only depends on theta because r1 is fixed along this curve. And similarly on this outer circle, so you can provide this data as a temperature you can fix, you can maintain this temperature all along this curved line. So, if you want to solve this problem by the separation of variables method, that is the technique we have mastered so far. So, we need two boundary conditions. So, you look for so this is the data is given on for r variable and when r equal to r1 and r equal to r2. So, what you get is you extract try to extract a Sturm Liouville problem. So, here in this case what we see is earlier for the annulus region it is already intrinsic. So, you have for theta variable you have a Sturm Liouville problem and so we do not use any boundary condition because it is a complete circle. So, you have a theta that is actually same at 0 to 2 pi. So, you have intrinsically you have a periodic Sturm Liouville system, but here if you want that and you see that this is for theta variable when you extract the Sturm Liouville problem. So, you have two more boundaries, this is the one boundary and this is another boundary, that is at theta equal to theta 1 and theta equal to theta 2. So, at theta equal to theta 1 you have to provide 0 boundary condition. So, that is the temperature you maintain at 0 and here also you maintain some other 0 temperature here. So, if you give this as a Dirichlet data we can expect a Sturm Liouville problem. So, regular Sturm Liouville problem for theta. So, that is what we will see. So, we will try to solve in this domain. So, we will write it as a problem and then so we will try to write this as a problem. Okay. So, we just redraw this area. So, what you get is this. So, this is your part of this annulus region. So, you have 0 here. So, if you say 0, this is 0 and this is your R1, R equal to R1 is this curve and you have this is x axis and you have this makes theta angle theta 1 and this makes theta 2, this line, okay, and this is R equal to R2. So, on this boundary you have u is 0 and on this boundary also u equal to 0, okay, and only here you have to provide this data. So, u is some function of theta, so that is f1 of theta and here u is you give some data f2 of theta. So, if you inside this domain this is your D in which you satisfy the Laplace equation. So, let us write this uxx or urr. So, there is a Laplace equation in polar coordinates. This is a curved domain, so circular domain. So, we can have Laplace equation in polar coordinates urr plus 1 by r ur plus 1 by r square u theta theta equal to 0. So, the domain of the differential equation is, partial differential equation is R1 and R2, and theta is between theta 1 and theta 2. So, this is the partial differential equation, this is the Laplace equation in this domain. Now, you have to provide the data. So, you can give the boundary data, you have u at theta 1 or theta 1 equal to 0, and also u at r theta 2 is also 0. So, this is the boundary conditions, and you can also give other boundary conditions like u at r1 theta is f1 of theta, and u at r2 theta is f2 of theta. So, here theta is between theta 1 and theta 2. So, here r is between r1 and r2. So, this is your boundary data, you want to solve this problem. Okay. So, this is the boundary value problem for the Laplace equation. So, how do we solve? So, solution procedure which you know, you start with the separable form of solution, let u of r theta as you look for capital R of r, capital theta of theta as a non-zero solution. If you substitute, what you get is r double dash of r plus 1 by r dash of r, okay, with theta of theta, that comes out as theta of theta as a, if you substitute into these two terms, equal to minus 1 by r square theta double dash of theta into r of r. So, if you substitute into the remaining part and take it to the right hand side. So, this is what you have. So, this implies, now you divide with both sides with r of u of r theta, that is r of r into theta of theta. So, theta goes, what you are left with is r double dash of r plus 1 by r dash of r divided by r of r, bring this minus here and this you write it as, now the right hand side becomes theta, and you can bring this, you can write this 1 by r square times and theta of theta. Okay. Now, you can bring this r to the other side. So, you have r square here and this becomes r. So, this is what is this. Now, left hand side is a function of r, right hand side is function of theta. So, it should be constant, okay, unless two independent variables are same as a functions, okay, unless they are, so those expressions should be constant. So, this is what you have. So, this is what is what you get. So, the Laplace equation becomes two ordinary differential equations. One is r square r double dash of r plus r times r dash of r plus lambda times r of r. So, this is Euler-Cauchy equation. This is between r is r1 and r2. This is 1, and for theta, so theta double dash of theta minus lambda theta of theta equal to 0. This is in the self-adjoint form, you can easily see as 1, p is 1, q is 0, equal to lambda times w is 1. So, your dot product you can define as a dot product as what is the domain? Theta domain is theta 1 to theta 2, okay. So, theta is between theta 1 and theta 2. So, for that reason the domain is this, and you have phi x psi x bar dx. So, this is the dot product you define. So, now you apply this boundary data. So, boundary conditions are u at r theta 1 equal to 0, which gives me r of r into theta at theta 1 equal to 0. So, that means this constant should be 0, r of r cannot, as a function cannot be 0. So, this implies theta of theta 1 is 0. So, this is the boundary condition for this ordinary differential equation. Similarly, you get r 2 theta, r theta 2. So, other boundary condition r theta 2. So, homogeneous boundary condition, you will get theta of theta 2 will be 0. So, these are the two boundary conditions for this. So, what you extracted is as regular Sturm Liouville problem. So, this is the ODE with these boundary conditions, this is the regular Sturm Liouville problem. So, you can find the solutions. Okay. So, let me write the regular Sturm Liouville problem. Problem is for theta. So, theta double dash of theta equal to lambda theta of theta. This is theta is between theta 1 to theta 2, and what you get is theta of theta 1 equal to 0 at theta of theta 2. So, what are the eigenvalues and eigenfunctions? Eigenvalues and eigenfunctions you need. So, what do you get? So, what are the eigenvalues and eigenfunctions? If you actually see earlier, we have actually solved this Sturm Liouville problem, and from which you can see that the eigenvalues are eigenvalues. You can see that lambda is, I will just give you the lambda is lambda equal to minus n square pi square minus n square pi square divided by theta 2, which is bigger than theta 1. So, theta 1. So, this is what you have as a square. Okay. So, these are your eigenvalues, and eigenfunctions are, so what you get is eigenfunctions. These are your eigenvalues, n is running from 1 to 3 onwards, and eigenfunctions, what we see is as this depends on n. So, I am labeling this eigenvalues as lambda n, and if you call this eigenfunctions as theta n's, theta n of theta as sine n pi by this is n pi, I will just n pi theta minus theta 1 divided by theta minus theta 1. So, theta 1 is smaller. So, divided by theta 2 minus theta 1. So, these are your eigenfunctions. Okay. So, you just look back. So, earlier we have solved this for y double dash equal to lambda y, theta is x is now between, y is a function of x between a to b, and you have y at a equal to 0 at y equal to b. For this, what we found is lambda equal to minus n square pi square by b minus a whole square as your eigenvalues, and eigenfunctions are yn of x. These are simply sin n pi x minus a divided by b minus a, or also sin n pi x minus b by b minus a. That is also possible, but that is simply constant multiple of this. So, we can take this as eigen. Okay. They are dependent. If you take x minus b here, sin n pi into x minus b by b minus a. If you take that function, that is also simply constant multiple of this function. So, in that sense both are, if you consider so what I am saying is n pi x minus a by b minus a and sin n pi x minus b divided by b minus a. Both these functions are eigenfunctions, but they are constant multiple of other. Okay. They are actually dependent. So, you can consider any one of them. So, I choose this one. So, in that sense, if you just do it here, so that is what I have written here. So, these are eigenvalues and eigenfunctions for this Sturm Liouville problem. So, for n is running from 1 to 3 onwards. Now, you look at this Euler-Cauchy equation, another ODE for this lambda n. So, if you write that r square capital R, for each n I am labeling it as Rn double dash of R plus R times Rn dash of R plus lambda is now minus n square pi square by theta 2 minus theta 1 whole square into Rn of R. That is what is equal to 0 for theta R is between R1 and R2. So, this is the Euler-Cauchy equation. So, you for each n is running from 1 to 3 onwards, you have this many number of ordinary differential equations. So, you have Rn of R is, we know that if you can look for solutions of the form r power m. Okay. if you look for r power m as a solution, and what you see is you get m into m minus 1 plus m minus n square pi square by b theta 2 minus theta 1 whole square, okay, and this into r power m equal to 0. So, if you simply substitute this into this equation, what you get is this cannot be 0. So, you are looking for non-zero solution, and so that means m square minus n square pi square by theta 2 minus theta 1 whole square equal to 0. So, that gives me, since n is running from 1 to 3 onwards, this is cannot be non-zero. So, you have two different limits. So, plus or minus n pi by theta 2 minus theta 1, there are two roots, n is running from 1 to 3 onwards, because 0 is not involved. So, you do not have repeated roots. So, the solutions are, so I can write directly. So, you have two repeated roots. So, the general solution is, so the general solution is, I can write the general solution now. If you know two linearly independent solutions, one is with positive, other one is the negative root. So, you have a n is a constant and r power m. So, r power n pi by theta 2 minus theta 1, this is one, and then plus b n r power minus n pi by theta 2 minus theta 1. So, this is the general solution of this equation, okay. So, for this is true for every n. So, what you got with this solution. So, now I know r n of r and theta n of theta. So, you can make a product and write your solution. So, let me write that solution u n of r theta for each n which is running from 1 to 3 onwards, we have the solution. So, u n of theta is r n of r a n times r power n pi by theta 2 minus theta 1, that is the power, okay. So, b n times e power minus n pi by theta 2 minus theta 1, this into, and what is theta n of theta? So, that is sin n pi, you can write this sin n pi theta minus theta 1 divided by theta 2 minus theta 1. So, this is the function of r and theta. This is not exponential, this is r power of that, okay. So, if for each n, this is the solution that satisfies the Laplace equation inside the domain and that two boundary conditions, okay. So, this boundary, these are the boundary conditions, those are boundary condition 1 and 2, okay. What we have written is boundary condition 1, this for each n, u n satisfies this equation and the boundary conditions here. So, still you have not, they are not satisfying this thing, the other two boundary conditions. So, you superimpose, let u of x t, u of r theta be the superposition of all these solutions, n is from 1 to infinity, u n of r theta. That is, now I can make a superposition, even if you take a constant here, that constant into this constant will be another arbitrary constant. So, that is why I did not write here. So, n is running from 1 to infinity. So, you have arbitrary constant is a n r power n pi by theta 2 minus theta 1 plus b n r power minus n pi by theta 2 minus theta 1, this into sin n pi theta minus theta 1 divided by theta 2 minus theta 1. So, this is what is the, let this be the solution, the general solution, okay, solution of the Laplace equation with boundary conditions 1 and 2, okay. Boundary conditions like u at r theta 1 equal to 0, also u at r theta 2 equal to 0. So, satisfying these two boundary conditions, okay. These are the things. So, that satisfies this. Now, you want to, it also need to satisfy the other boundary conditions. So, apply the other boundary conditions, other boundary conditions, what are those? U at r1 theta equal to u at r1 theta is f1 of theta. So, you apply that. So, if you apply, what you get is if you apply that. So, u at r 1 theta is now you have this summation, n is from 1 to infinity a n. What happens, r power you have to replace r is now instead of r power you have r 1 power n pi by theta 2 minus theta 1 is simply a constant plus b n r power minus n pi by theta 2 minus theta 1. So, this is also r 1, you substituted in the place of r 1 theta, and now this sine n pi, now we are putting theta as it is. So, you have this, these are your eigen functions, theta minus theta 1 divided by theta 2 minus theta 1 equal to f 1 of theta. So, now these are your eigen functions. So, you can make a dot product both sides with these eigen functions. So, that you can get a n times this constant, this whole constant r 1 power n pi by theta 2 minus theta 1 plus b n r 1 power minus n pi by theta 2 minus theta 1. This whole arbitrary constant I can get it as integral. Now, theta is between theta 1 to theta 2, that is a dot product. When I make a dot product with f 1 with this eigen function. So, what you get is f 1 theta into this bar of this function. So, that is these are all real valued functions. So, bar does not matter. So, n pi theta minus theta 1 by theta 2 minus theta 1 d theta, that is the right hand side. The left hand side what is remained is only the integral theta 1 theta 2, so itself. So, that is sine square of n pi theta minus theta 1 divided by theta 2 minus theta 1 d theta. Okay. So, this actually we can actually calculate. So, that is half of okay. So, you can evaluate this. Okay, I will not evaluate now exactly. So, this is one equation. So, let us call this one equation. Okay. Now, we apply the other boundary condition u at r 2 theta equal to f 2 of theta. This is 1 and this is 2. So, these are the remaining two boundary conditions. If you apply, so everything is same. So, you get the same equation with r 1 is replaced with r 2, f 1 is replaced with f 2. So, what you get is we get by the same procedure we get a n times, in the place of r 1 you get r 2 n pi by theta 2 minus theta 1 plus b n r 2 power minus n pi by theta 2 minus theta 1. This is equal to, now the right hand side instead of f 1 you put f 2. So, theta 1 to theta 2 f 2 of theta sin n pi theta minus theta 1 by theta 2 minus theta 1 d theta. This is one integral divided by other integral, that is a constant theta 1 or theta 2. So, sin square n pi theta minus theta 1 divided by theta 2 minus theta 1. This is for the sine of this sin square d theta. This is the equation number 2. Okay. From 1 and 2, so you can easily see that. So, what you required in this solution, only a n's and b n's are unknowns. Okay. So, you can get a n's and b n's from the C, these are unknowns a and b n, a and b n with constants. These are constants. This right hand side whole thing is one constant, this is another constant. So, you have two linear equations 1 and 2 with for the unknowns a n. So, solve 1 and 2 to get a n and b n, that is it. So, once you get a and b n you substitute here. So, this is the general required solution. So, what I am putting as a in this box is the general solution. This is the solution, this is the required solution. Okay. Once you get this, once you get this a n's b n's and substitute here, that will be the general solution of, that will be the solution of the boundary value problem that we have considered. Okay. So, that is how you solve this. This is the procedure is something exactly similar to what we have done for the full semi-annulus full annulus region that I have solved in the last video. Okay. So, once you know this solution here like this, now I can make many things. So, this is R1 and this is R2. Okay. So, now the next problem. So, what are the problems you can extract out of this is consider suppose you have a suppose you have first and foremost is this one. So, you try to make R1 equal to 0. If you do that, R2 and this becomes a sector, simply sector. So, you have R1 is 0 and R2 is, so R equal to R2 is something else, okay. R equal to 0 here and this is the one. So, here you still need to, this is the boundary and this is the boundary, and here you provide here. So, u equal to f2 of theta and u equal to 0 here and u equal to 0 here. So, u at r of r comma theta 1, this is theta 1 and this is theta 2. So, you have at theta 1 theta 2 you have a homogeneous boundary conditions. Then the solution is what? So, this eigen functions are all same, eigen functions are all fine. So, they are all same. So, this is no change here, okay, because theta. So, ordinary differential equation for theta is same. So, on the boundary conditions, these two boundary conditions if you apply, you get the same Sturm Liouville problem and you get the eigenvalues and eigen functions. So, only thing you have to see is this equation now becomes a 0 to, I will write it in a red. So, 0 to r is between 0 to r2. So, this is what you will see, and because of this, but you see if it is a plate, a sector kind of plate, and you maintain these temperatures here and then this curvy boundary, and at 0 it cannot be infinity. So, if r is 0, r equal to 0, you cannot have a infinite solution, okay. So, when you write this, when you find the solution and you see that this is the solution, this is the temperature for each n, and because it has to be bounded at r equal to 0, at r equal to 0 this is going to be infinity. So, that means bn's are 0, bn's will become 0 and implies, so you superimpose all these solutions. So, finally you get the solution is un is only this one and this one, okay. So, an times r power n pi by theta 2 minus theta 1 into sin this eigen function. So, you superimpose all of them without this bn's, okay. This bn's you avoid, and what you get is only one sum an times of r1 into r power of this into sin of this eigen function. So, you apply only the remaining boundary is only now this one. So, this boundary if you apply, that is u at r2 of theta equal to f2 of theta. So, without this, so we get the second equation. So, the second equation without this implies you can find your an. So, this is a constant, an is simply this you can divide. So, that is what is your ans. Once you know ans, you know everything here, okay. That will be the solution of this sector problem, still this general sector. Now, the third problem, so you can look at is you can also consider you can now simply take theta equal to theta 1 equal to 0 and theta 2 equal to pi. So, what is this region? This sector becomes, that sector, full sector becomes now, this is simply, this is like a semicircular region. This is your domain D, you provide u at r2. So, let us say r2 theta is f2 of theta on this circular circle, and now this is 0 and you have theta. So, you have theta, this is exactly, you have r theta 1, that is 0. So, that is 0 equal to 0. So, here and here you provide 0 boundary conditions, u at r pi equal to 0. So, the temperature you maintain here as a 0, that is I am seeing as two boundary conditions for theta equal to 0 and theta equal to pi, okay. Between r is between 0 to r2. So, if you do the same thing, procedure is same, only things here you can directly get ans are this, only difference is theta 1 theta 2 you take it as 0 to pi. If you take 0 to pi, only change in this reduced solution, okay. For this problem you take simply theta 1 theta 2 you change, you will get, you solve this problem, okay. And now if you take theta 1 equal to 0 and theta 2 equal to pi by 2, so what you can solve is this in the quarter plane, the sector in the quarter plane. So, that is also you can solve. So, this is how you can solve this kind of curved domains. Here theta u at u of r comma theta 1, that theta 1 is 0. So, 0 is 0 and you have to provide 0 condition here. So, that is r pi by 2 equal to 0. If you are given this problem, so that is exactly the same problem you can solve. So, ANs, only thing is ANs will contribute. So, the solution will be this without this term. So, you have ANs are actually calculated from this, from the second equation. Okay. Only thing is theta 1 theta 2 you replace with 0 to pi or 0 to pi by 2. So, to solve these two different problems. Okay. So, like that, so only certain domains you can solve these problems, only in this using polar coordinates, only some circular domains you can solve. Okay. So, that means some circular domains means this is in this, suppose you are given different things. Okay. Suppose this is non-zero, some A, some let us say some C1, I maintain some non-zero temperature C2. What you have to do is you try to use some transformation, maybe something like you extract, you basically you write U as V plus U1 plus U2, okay, or V plus some psi is a function of x alone, and this is function of xy. If you do this, you may be able to find, if you can find such a V that satisfies these non-homogeneous boundary conditions. So, that V satisfies homogeneous boundary conditions here, and this may be little different, but this is something else. Okay. So, like that, if you, the idea is if you have a non-zero conditions, if you can reduce by some way to the problem with the homogeneous conditions, that is 0 0, then you know its solution, so that you can solve even for the non-homogeneous conditions. Okay. Non-homogeneous boundary conditions. So, this way, this is the separation of variables method, which you can apply to solve certain Laplace equation in certain domains, either it is a rectangular domain, we have seen that it is a finite rectangular domain. So, it is a rectangular domain or a semi strip domain. Okay. So, we have seen the semi infinite strip domain. Okay. And also for the curved domain, so circle, inside the circle, exterior of the circle or annulus region, and also here in this sector, on a sector, or in the semicircular domain, or a sector in the quarter plane. Okay. So, like this you can solve a Laplace equation, that is actually steady state heat equation. Once you reach the once the plate, okay, the two dimensional plate, once it reaches the steady state. Okay. So, by keeping the temperature at the boundary, fixing the temperatures at the boundary, so you can solve these problems. So, what else we can do? So, we are so far for this Laplace equation we have only provided for this curved domains, what we have provided only temperature at the boundary, we only provide the Dirichlet condition. But you can also provide the normal data. So, what is the normal data here? You can provide Ux. So, that is something like U theta. Okay. This is U theta is your normal theta. So, here U, so suppose see, this is the boundary and this is the boundary and this is the boundary. So, whatever you extracted, so Sturm Liouville problem when you extracted, what you have is you provided. Here you can provide dou u by dou n equal to 0 at r comma theta equal to 0 is 0. So, what is that thing? That normal thing you have to find out. Okay. So, what is the normal here? This normal in polar coordinates you have to provide that as a data here. Okay. Similarly, you can provide this dou u by dou n here 0. So, that means you insulate these two ends, still you can extract Sturm Liouville problem, because these are homogeneous boundary conditions. Okay. And only the thing is that you have to have finally you can do this. Here also suppose you want to do this, this is normal is only r. So, you have u r, clearly I can see that u r, this is the normal is this r, right, this normal vector is r simply. So, dou u by dou r is the normal here for this circular domain. So, if you give this one together, so it should have from u r of r theta r2 comma theta is from 0 to pi by 2 has to be 0, this has to be 0, this is the necessary condition for you to have. So, you insulated, so you have not insulated here. So, the insulation here you are giving some external source. So, whatever comes in should go out. If you are providing a heat inside some part of it, some part of it should be able to go out. So, that eventually that effectively net flux of through this surface, through this boundary, the net flux of the temperature should be 0. Okay. So, in that sense, so anyway here it is 0, flux is 0, insulated here the only boundary through which you can either allow the heat to inside or to go out. So, effectively that flux, heat flux should be 0. So, that is the necessary condition. So, you can provide these insulating boundary conditions, but only thing is you have to maintain a 0 flux net flux of the heat, so that you can solve these boundary value problems. Okay. Otherwise you cannot. So this is how we have solved this Laplace equation in certain domains. Okay. So this is how you solve Laplace equation in curved domains. Thank you very much.